All right, so good afternoon, everyone. Let's share my screen. And let's quickly wrap up this chapter on number theory. So there were, I think, two smaller things last time. So on this slide, I think at some point I noticed that when I watched the audio track or when I watched the video or when I went over the video of the last lecture, at some point I said that Q without zero only has this H here as a subgroup. That's not true. That's H is the only finite subgroup. Right, so what was in my mind was H is the only finite subgroup, but that's not the only subgroup. So there I need to correct myself. For instance, let's quickly make that another subgroup of this. Let's use another color. Could, for instance, be the following. Let's say we just take the set of 2 to the I, where I is in Z, right? That's obviously a subgroup, and you can construct a lot of a multiplicative subgroup, and you can construct, of course, any numbers. Let's call this maybe H prime, but that's an infinite subgroup. Right, so if you multiply powers of 2, can be positive, can be negative powers, it will always stay a power of 2. And of course works for any other prime, for any combinations of such groups. So good. That is that. The other thing was, where is it? Here. Now, corollary 4, this is really a very simple idea where we say if G is a finite group and has prime order, then it is cyclic, right? And the idea is to take any take any G which is different from 1 in G, and just look at the cyclic group generated by G. If this was a subgroup, then so this will be a subgroup, the group generated by G, right? We typically write that. So if we have some G in G, then we typically write G as cyclic subgroup generated by G, right? All powers of this G. And corollary 3 said, well, either this subgroup now just consists of 1, or it's directly the entire group. But we said G is not equals 1, and G is in this subgroup, so it must already hold that by corollary 3 that the group generated by this lowercase g is already the entire group. Okay, good. That was that. Now we talked about primality testing and about cryptographic groups. And as an example, we have seen this group H here. This group H is also called the group of quadratic residues. modulo P. Right, and we knew that if P is a so-called strong prime, so if P minus 1/2 is also a prime, we call P a strong prime. Then H, this group of quadratic residues modulo P, is a prime order group. And we talked about this assumption 1 here, that computing discrete logarithms is hard. And this group H was, in fact, historically the first group for which this was conjectured, and it still holds. This was by a conjecture or assumption by Diffie and Hellman in the year 76, that D-log problem is hard in H. Okay, so computing discrete logarithms in this group H, we assume is hard. I mean, people have been trying for more than 40 years to break this. Now, there's of course always some cases and conditions to this, but at least in terms of classical algorithms, no one has found a classical algorithm which can efficiently compute discrete logarithms in this group for a large enough P, right? For a P which is a prime, or let's say P prime, where P prime is a security parameters bit prime. Okay, so this was historically the first group in which people conjectured this discrete logarithm problem to be hard. Then a little bit later in the 1990s, people were looking at another object which is really popular among number theorists, namely elliptic curves. So elliptic curves, here you see an elliptic curve over the real, are sort of a really let's say, fun little object on which you can compute a group law. So, I mean, let me maybe draw my own copy here, right? It doesn't look that good. But if you have 2 points, and now we have this third picture, 2 points on such an elliptic curve, then you get the guarantee that if you draw a line through these two points, then there's exactly a unique third point on this curve, on this elliptic curve, which is also on this line. So it means every line, so to speak, now in general, this needs to be conditioned, but every line goes through 3 points, unless the line is a tangent, right? Tangents only go through 2 points. So this is a group where operation is addition. Now I'm currently explaining this. So elliptic curves, when you take any 2 points and draw a line through it, then you will find a third point, right? So if you call this point A, this point B, and now you get a third point. And the thing about elliptic curve groups is, if you now take this point and reflect it on the x-axis, you get a point C, then this now becomes a group law. So A is a point, B is a point. Now we can write C is A plus B, right? So the result of applying this group operation is on A and B is C. C. And you can really check that this is a group operation. Now, first, I mean, the easiest thing you can check is that it commutes, right? It doesn't matter if you add A and B, you always get C. But when you have a group, we need to check a few things. The first one was we need to check for an identity element, and this is not so easy to visualize. The identity element is the so-called point at infinity. So in a certain sense, if you I mean, to do this properly, I would have to talk about projective geometry, which is completely out of scope of this lecture. But you can think of basically if you, whoops, if you have 2 points, right? P and minus P and minus P. Then the line through them is parallel to the y-axis. So we say that this parallel line intersects the curve at infinity. So we call this infinity element also O. You can think of it this way: if you were to move P slightly a little bit to the side here, this point at infinity would become a finite point. But when P and minus P are opposite to one another in the on the x-axis, you will have no more intersection with this curve at a finite point. But then we say, okay, let's just define it. It intersects this curve at infinity. And you can even make this precise, right? So it sounds like maybe a little bit math mumbo jumbo, but when you switch from Cartesian coordinates, as this is drawn here, to so-called projective coordinates, then you can really make this precise to say that, okay, the vertical line intersects this this curve at infinity. So, and now you can tell on such an elliptic curve, basically the inverse group element is always the opposite element on the y-axis. Let me ask, what is it about this point here, right? He doesn't have a point opposite on the y-axis. So what's the deal with this guy? Anyone? Conjecture? Let me maybe close the windows. Out there. It's the neutral element. The inverse is itself. It's its own inverse, and that's correct. So this point, this is a point with a self-inverse. Point is self-inverse, but not the identity, right? But not identity. Again, the identity, think about, that's a point at infinity. Good. So there's, in these elliptic curve groups, we have one point who's a self-inverse. And typically, when of course, when we want to do crypto, if we have such a point, not always have it, we need to throw it out, or because in certain applications, if we had such a point in the curve, this could make trouble. Now, good. This is the group law on these elliptic curves. I haven't even really said how to describe them. And the way to describe them, here's a different one, is using certain cubic equations over R, right? And that's typically how we draw these elliptic curves. Here you see one which consists of two connected components. The one above here only has a single connected component, but still, even if you have two such connected components, you still have the same group law. But that's how they look over the reals. Now when we actually want to do crypto with these elliptic curve groups, we define them over a finite field, right? And then all this, and then you see this picture here, then all this nice visualization is out of the window. You can still think that every line through such 2 points, now you need to be careful, a line in this finite field, C89, wouldn't correspond to a two-dimensional line here. But again, over that field, you still have this property, but you don't have nice visualization anymore. So this is essentially the reason, right, why in all these introductions, when people talk about these elliptic curves, they show them over the reals. But here's the thing. So we need elliptic curves in which the discrete logarithm problem is hard. And in those guys here, over the reals, it is not hard. So here you have a d log, because it's continuous, not hard. Whereas here, d log conjectured to be hard. In fact, these are currently the most popular cryptographic groups, because if we go back to the last picture, this group of quadratic residues modulo p, over time, people have found attacks that are not polynomial time, but that do better than expected, right? So for these groups, attacks were found that were better than what people originally conjectured. In fact, people have found so-called sub-exponential attacks. In the beginning, people conjectured that it would take exponential time to compute a discrete logarithm, but then over the years, sub-exponential algorithms were found. Whereas here, for elliptic curve groups, currently, for certain elliptic curve groups, the best algorithms that we know, for some of them, the best algorithms that we have run in exponential time. So here you can assume that computing discrete logarithms is exponentially hard without contradicting something, and cryptographers do this. Okay, so and finally the last thing. I mean, we have talked about generating primes, and related to generating primes is, of course, if I give you a number, then break it down into its prime factors. And this is the so-called factoring problem. So in a way, this is the other basic assumption in number theoretic cryptography, namely that factoring large numbers is hard. When I say factoring large numbers is hard, which large numbers do I mean, right? I could give you some large number, which is kind of obviously a power of 2, right? This is something that can easily be detected, and factoring this is not hard. But people have been studying this problem since antiquity, right? And to date, we have no efficient classical algorithm which, given any number, breaks it down into its prime factorization, right? Any factorization algorithm with good worst case runtime. But now we know that worst case problems are not good for crypto, right? We need sort of something with average case hardness. And this is where sort of we need to settle on sort of certain distributions of numbers. And people have already written something on the chat right now. So what cryptographers settled is sort of in some sense worst possible scenario for an adversary. Namely, we look at numbers n, which are the product of two big primes, right? So the factoring problem or factoring experiment is phrased as follows. So we have an adversary or algorithm A. We choose two large primes, two lambda bit primes, P and Q, multiply them together, and get this n. And now this n is being given to our algorithm A, who returns P prime and Q prime. And if P prime times Q prime equals n, output 1, otherwise 0, right? The way the reason I'm writing this with P prime and Q prime is the order of these two things could be flipped. But of course, the prime factorization of n is unique. Now we say now we get the following assumption, the factoring assumptions, which says that for every PPT, for every efficient algorithm A, it holds that the probability that A wins this experiment is negligible. Where, of course, this probability goes over a random choice of P, Q, and random coins of A. Okay, so someone asked in the chat, it is proven that this is an NP-complete problem, right? Conditionally right. So one can define a version of the factoring problem, which turns out to be NP-complete, but it's not this problem. And it even turns out this NP-complete version is not useful for crypto at all. So the version of the factoring problem that's proven NP-complete has in fact not a number theoretic, but a more combinatorial flavor. So the hardness comes from something slightly different. So this problem here is not NP-complete. And in fact, sort of the whole complexity community would be shocked if it was NP-complete, because this factoring, let's say factoring, the way I defined it here is in NP. That's true, right? To find find a witness, you just guess P and Q, but it's also in co-NP, right? And this is sort of, for complexity theorists, a red flag. If a problem is in NP intersect co-NP, no complexity theorist believes that such a problem can be NP-complete, because that would have dramatic consequences, like the collapse of the polynomial hierarchy. But this is also stuff that's out of scope for this lecture. All right, I'd like to finish with that now. Are there still any questions regarding this, or can I then move on to the next segment, essentially? See if someone still has a question regarding this. All right, I don't see a question, so let's move on. let's talk about how to put this stuff to practice. Namely, let's talk about key distribution and key exchange. All right, so we're still in this quadrant of public key encryption. And let's quickly recap private key cryptography. So private key cryptography, we can think of a technology which comes from a time when computers were huge, when computers were not ubiquitous. There were sort of very few computers in the world. So it was kind of a good assumption that these computers maybe belong to the same company, and there was some way to distribute private keys of private key encryption schemes securely to these computers, right? They come from or that's a technology from the early digital age when computers were rare, and everything was fine, right? Because I mean, who would you want to communicate securely with anyway, right? If there's only that many other computers in the world. So, however, since the 1980s and especially since the 1990s, things have changed rapidly, right? So where in the 1960s, there was only a demand for secure communication between a very small number of data centers. These days, I mean, you can communicate digitally with people all around the world, right? And there's not just a small set of possible people you can talk to, but in fact, billions, right? There's billions other devices you could possibly talk to, and pre-establishing some keys with every single one of them with people you haven't ever met before, right, is completely unrealistic. So in the old days, the assumption was that anyone you're communicating to, you've in some form met already. But since we have global digital communications, this is an assumption that's just not valid anymore, right? There might be offshore banks, there might be devices in other countries, so that the parties you're communicating to don't even have to be real people. They can be servers or IoT gadgets distributed somewhere around the globe. And still, you do have a need to communicate securely with these people and these devices. So the old assumption that we do have a way to manually distribute private keys was clearly outdated. That was in the 1970s, still before the invention of public key cryptography. People started thinking about this problem, and they came up with a sort of a modest solution called key distribution centers. So the idea here is the following. You have a central entities which manages and distributes keys. Say we have three parties here, say Alice, Bob, and Charlie. And the one thing we assume is that each user has a joint key with the key distribution center, right? So Alice has a key KA, Bob has a key KB, and Charlie has a key KC. And the key distribution center also knows these keys. So what does the key distribution center help now? Maybe first we can assume that all these keys were generated by the key distribution center via a pseudo-random function, right? Then that means it doesn't need to store all these keys for its users, but it only needs to remember their names to generate them pseudo-randomly. And it also needs to store this tiny PRF key. Good. But now let's say, okay, now Alice, Bob, and Charlie have the ability to securely communicate with the key distribution center. Now we could just say, oh, let's route all communication through the key distribution center, right? Alice wants to talk to Bob. Let's just have her talk to the KDC. KDC decrypts, learns what Alice wrote, and sends the message to Bob. Well, this is bad for several reasons, right? Now, this key distribution center, which needs to be hardened, which needs to be protected, becomes a communication bottleneck. You don't want to route all your communication through a single server. So this is not what we want to do, right? Instead, we can, oops. Interesting. Yes or no? Okay, so now something is frozen. Let's start this again. Okay, so instead we're gonna do the following. Let's say A wants to establish a secure channel to B. Alice wants to securely talk to Bob. Then we're gonna do the following. Alice sends a message to the key distribution center, telling it, I want to talk to B. So what the key distribution center now does is it generates a new private key, K, and sends encryptions of this key under both KA and KB to Alice. So Alice gets two ciphertexts, one under her own key that encrypts K and one under Bob's key. So of course she can now decrypt this ciphertext that was meant for her and get the key K. Furthermore, she can send this second ciphertext, which encrypts K under KB to Bob. Bob can decrypt K as well. And now we have established a key between the two, and they can talk securely to one another without ever resorting to the KDC again. Good. So there's a question on the chat. Do we need a KDC because we don't want to reuse keys? I missed that part. No, the reason we want a KDC is because we don't want to assume that Alice, Bob, and Charlie already have session keys with each other, right? So Alice and Bob need to have the same key K, but they have different keys. Alice starts off with a key KA that it got from the KDC. Bob starts off with a key KB. Now we want to establish a joint key. And for that, we're going to use the key distribution center in this way by letting it generate a fresh key, encrypt it under both KA and KB, send this to Alice, and she can send this encryption of K under KB to Bob. Good. Next question is, why can't we use public key encryption? I can tell you that. When this was proposed, public key encryption was not invented yet. So this was before the invention of public key encryption. And here you also have the major problem. The key distribution center is the single point of failure. If I break into the key distribution center, then I know the keys of all the parties involved and all security is gone. Good. So there's another question in the chat, but how do KDC and Alice agree on KA security? Do I still have, oh, no, don't have a point there. The idea is that once you let's say, start your job at a new company, you once manually go to the KDC and get your key, right? So to establish a key with a KDC, you need a secure channel, like send it per post or whatnot in a sealed envelope. That's how you get your key. There's another comment: KDC could also decrypt all messages. No more privacy guaranteed. Am I right? That's correct. You need to trust the KDC in this setting. So you see, there's many drawbacks, but this was sort of the best thing that you could do before the invention of public key encryption. So in particular, KDCs don't solve the key distribution problem. Key distribution problem in open systems, right? So you first need to register yourself with the KDC. And now we're in the year 1976, when these two gentlemen, Whitfield Diffie on the left and Martin Hellman here on the right, wanted to go new ways. So basically, their starting point was that in nature, many physical processes are asymmetrical. Many physical processes are asymmetric. Think about a padlock. If I give you an open padlock, then you can easily close it, right? You just press this handle into this hole, and then it's closed, but you can't open it anymore. So that's a physical system. That's one way. Or think about a vase. When you take a vase and shatter it and smash it on the floor, it easily springs into 1,000 pieces, but putting the pieces back together is infeasible, right? So here you have sort of processes where you can easily do something in one direction, but the other one is hard. For the case of for the vase, putting it back together is generally hard, but for the case of the padlock, if you're in possession of the key, you can open it up again, right? So if you have some additional secret information that's specific to the padlock, you can open it up again. Good. And their idea was really, starting from that padlock ideas, to implement this digitally. They wanted to exploit a computational phenomenon with this same property to establish a key remotely. And you guessed it, now we're talking about the Diffie-Hellman key exchange. So what we need for that, we need a cryptographic group G of order P. Cryptographic group means that at least the discrete logarithm problem is hard in this group. Will turn out to be insufficient. This is not sufficient to have that D-log is hard, but if D-log is easy, anything that I'm saying now is insecure, right? So this is necessary but not sufficient. So let's take a cryptographic group G and recall G can be either this group of quadratic residues, mod P, right? The first one I've been talking about, and the use of this group was actually suggested in this original paper by Diffie and Hellman. Quadratic residues modulo P, or elliptic curve groups. Good. What are we going to do? So Alice first generates a group G somehow of prime order P with a generator G. So this group, of course, if it's a prime order group, it's cyclic, and we have sort of any element in this group is a generator, and she just fixes a generator. What does she do then? She chooses uniformly at random an integer, a modular integer a in ZP, and computes this HA as G to the A. Good. Then she sends a description of this group, right, which consists of, I mean, the generator here is explicit. Whatever description for the group we have, it should at least include the order of the group, which is P in this case. But more importantly, she sends this G and this HA. Okay. Bob chooses a uniformly random B in ZP and computes this HB as G to the B. Now he sends HB to Alice. And now the two can do the following thing. Alice can compute a KA as HB to the A, and Bob can compute a KB as HA to the B. Now I say, great. Now they got two different keys. Now they've run a protocol, and now Alice has a key KA, Bob has a key KB. So what's the point of this? Whoops. Well, the point is this. So if you have your KA, this is HB to the A. Let's write this out. This is G to the B to the A. But just by simple exponentiation law, this is just G to the AB. All right, and of course, G to the AB, we can also write as G to the A to the B, which is of course HA to the B, which is KB. And voila, we see they have agreed on the same key. And really all we have used is that exponentiation in cyclic groups simply commutes, right? HB to the G to the B to the A is the same as G to the A to the B. There's more questions on the chat. Would a CPA encryption be enough for the KDC, or do we need CCA? That always depends on your attacker model. If you have an active adversary, you need a CCA encryption scheme. So if you have an adversary who manipulates encryptions, you need CCA security. Whereas if you just have a passive adversary who just eavesdrops, CPA encryption is enough. So really this depends on your threat model, so to speak. But good, so now we have Diffie-Hellman key exchange. Now I've shown you I've done something in reverse order. I've first shown you the protocol, and only now will I define what a key exchange protocol formally is, right? So far, we've basically said, so here's first the syntax, and here's a protocol that does it. Here, I mean, for historical reasons, and because you've all probably seen the Diffie-Hellman key exchange protocol already, we've started with the actual protocol. But now let's try to formalize what a key exchange protocol actually is. So the key exchange protocol Pi consists of the algorithms and instructions for both Alice and Bob, which output a private state and output a message which is to be sent to the other party. And we will call T just the public transcript of the protocol. So in the case of Diffie-Hellman key exchange, the transcript T is just this, right? Transcript. And the two algorithms are just the things that Alice does and the stuff that Bob does. All right, and we'll denote such a protocol run with just running the protocol pi, run this in a distributed fashion, and this provides us with a public transcript T and a key K, which is output by both parties. Good. And for the Diffie-Hellman key exchange protocol, we have three algorithms. LS1, let's go back. LS1 is just what's happening here. LS2 is what's happening here. And this is just, I think, Bob or Bob1. I'll just call it Bob, not Bob1. Let's delete the, one. Okay, good. So LS1 just produces this private state here, G and A, this first message. Bob produces as an output this key KB, and this message HB and LS2 just produces then the output KA. And the transcript consists of this, well, G, the generated G, HA, and HB. So correctness just requires that the two keys, the one generated by Alice and the one generated by Bob, are the same, right? We require that Ka is the same as Kb with probability 1. And of course, this can be weakened. But now let's get to the interesting part, namely security definitions for key exchange. How can we meaningfully define security, right? And again, when we define security, the aspects are what resources do we give to the adversary, right? What does he get to see? Does he get some oracles or something? And what's his goal, right? Those are the two important axes of security definitions: the adversary's resources and the adversary's goal. And now here's a definition. Let's say pi is a key exchange protocol, and we generate a transcript and a key, and we have and we choose another key, k hat, uniformly at random. Okay, and we now say that pi is secure against eavesdropping. Right, that says already something about the resources of the adversary. He can only listen to what's happened. If it holds for every PPT distinguisher D, that's our adversary now, that the smaller than negligible, that the probability that if I give to my distinguisher both D, T, and the key K that comes from this transcript, or the transcript and this fresh key K hat, which doesn't have to do anything with this transcript, if these two situations are indistinguishable for my distinguisher. There's one of these bars missing here. So let's maybe look at this in a picture. So here we have our distinguisher, and he has to tell two situations apart. In the left situation, he gets a transcript and a key which come from an actual run of the key exchange protocol. On the right side, he still gets a transcript which comes from the key exchange protocol, but the key that he gets, this K hat, is freshly chosen. Doesn't have to do anything with this transcript. And of course, the probability here is taken over the the random choice of T, K, and K hat, or the random coins of the protocol and K hat, so to speak. Whoops, and now jumped already ahead. But let's maybe quickly take a break and try to interpret this this definition. So what does this definition give us? So on the one hand side, the adversary gets a transcript of the protocol, which is public, which you can observe, and the key that comes out of this this protocol. On the right side, he gets a transcript and a fresh key. So what does that kind of remind us of? What definitions that we've seen in this lecture is this similar to? Good. So there's one comment on the chat. Intuitively, eavesdropping does not provide any additional information. I'd say that's actually, from my perspective, the correct interpretation of that, right? So if I give you that T, that transcript, it doesn't help you to it still doesn't help you to distinguish real keys K from let's say fantasy keys K hat that are never used. This is precisely the right interpretation of this. Now, of course, we can also take think about this more technically. This will mean that in security proofs, we will be able to replace K with this K hat. Of course, T is independent of K hat. Therefore, we can treat K hat as a fresh key, right? But that's again the same interpretation along the same line. Keys that are generated using the key exchange protocol look as if they're independent from the actual transcript. So there's another comment on the chat. This looks like a PRF where T is the key and K is the result. Sort of T is not the key, couldn't be something like the key because I mean you're getting T in the plane. So what you can rather think of T in the PRF setting is as some additional queries that you could make to the PRF, right? So PRF remains pseudo-random even if you have already seen many input-output pairs of this PRF. And in that regard, this definition is similar. All right, but again, let's quickly recap. So in terms of resources, we're actually giving the adversary very little. He can look at what's happening. He can observe a key exchange, but not much more. But in terms of goals, we're asking for the weakest thing possible, right? We're not asking him to recover the key K, but just to distinguish it from a random string. So on the one hand side, we're giving him in some sense some minimal resources, namely only a transcript, but his security goal is also, or his job in the end is also minimal. He just has to distinguish, right? He doesn't have to compute K. He just has to distinguish K from something uniformly random. Okay. Now let's look at the Diffie-Hellman key exchange protocol again. I mean, I told you already that security of this protocol does not follow from the discrete logarithm assumption. So I said that if the discrete logarithm assumption does not hold in this group, the protocol is necessarily insecure. But what assumption do we need for this protocol to be secure? Well, Diffie and Hellman were quite pragmatic. They basically made a new assumption and said, well, here's our they didn't say it like that, but that's sort of how we do this in hindsight. What's being done is we just take this protocol. Yeah, just take this protocol and we assume that it fulfills this security definition that we just made. That's the Diffie-Hellman, the decisional Diffie-Hellman assumption, the DDH assumption, one of the most basic assumptions in public key cryptography, right? And if you boil it down, what does the transcript consist of? Well, it has this HA, it has this HB, and you have the key K here. And here again, you have HA. Here, this is HB. But now this thing here is just G to the R instead of G to the AB. And if you choose R uniformly at random, then this K hat will just be an independent key. R in the P uniformly random. And this is a very nice and compact way to state that or to state the assumption that this key exchange protocol is secure, right? Oops. Now, of course, oftentimes when we write this assumption, we just leave this G away. So this is sort of the nice and compact way to write the decisional Diffie-Hellman assumption. G to the A, G to the B, G to the AB, which is the key that results from this transcript, is computationally indistinguishable from G to the A, G to the B, and G to the R, where this R is now just a fresh, or G to the R is a fresh random key. And to wrap this this up, if you sort of quickly think about what such a key exchange protocol does in real world terms, this is the following. Imagine you're sitting in a cafe at a table with two other people, and okay, now again a conversion error, but you can listen to what they're saying, right? So she starts the conversation saying, I want to talk in private, and then followed like with some random looking number. He says also agreed and follows with some random looking number. You hear everything in the plane, but then after that, you just hear gibberish. So you could hear everything that they were saying, right? The first messages, but then all of a sudden, at some point, you just hear noise. You just hear gibberish, even though they didn't have any pre-shared secret whatsoever. And that's sort of the magic of key exchange in real world terms. You listen to a public conversation, and at some point you don't understand anything anymore, even though those people talking to one another, they don't have any magic powers over you. So someone's writing sounds a lot like RSA, no, and someone else gave the answer, because RSA is also public key crypto. Yes, so really the reason for this slide here is just to provoke you to think what this key exchange stuff would actually mean in a real world setting, right? Or where does this weirdness come from, right? To see that something weird is happening or something unintuitive is happening, it's sort of instructive to think of the same thing happening in your everyday life, right? Same as in quantum physics. I mean, to think how weird things are there, it's instructive to think about thought experiments like Schrödinger's cat or whatnot. Good. But this is this, and let's quickly summarize what we've learned from this. So private key encryption is useful in closed systems with pre-shared keys, and in open systems such as the internet, we need a mechanism to securely distribute keys. So KDCs offer a partial solution, but really scalable solutions only came with key exchange protocols. All right, this is this. And we still have a little time. Let's go right into the next thing. Whoops. Here. Good. Someone still wrote a question on the chat. So what is the other big assumption in Diffie-Hellman's besides D-log hardness? I think I missed the point here. So good. Let me maybe just start this so I can write something. The assumption for the Diffie-Hellman protocol is, I mean, Diffie-Hellman protocol secure. This is in the end equivalent with a DDH assumption holds, right? So in a way, this is a very trivial statement. The decision of Diffie-Hellman assumption is just that this protocol is secure, right? So someone wrote it on the chat. Security is assumed, and because this protocol is so simple, or the underlying assumption can be written in such simple terms, this is a meaningful thing to assume, because when you write it as G to the A, G to the B, G to the A, B is indistinguishable from G to the A, G to the B, and G to the R. This is something, this is an assumption that can actually be cryptanalyzed, right? So you try to build algorithms which can tell these two ensembles apart. But so far, after more than 40 years of cryptanalysis, the best known algorithm that we have to do this is to compute discrete logarithms, right? When you give me this G to the A, G to the B, the best attacks that we have compute A from G to the A, draw a discrete logarithm here. And then once you have AB, check if this is the same as G to the AB or not. On that side, of course, R will with high probability be different from G to the AB. Right, so still after more than 40 years of trying to cryptanalyze this assumption, still the best thing we can do is computing discrete logarithms. But that said, some people still conjecture that in certain groups, the decision of Diffie-Hellman assumption and the D-log assumption or is implied by the D-log assumption, therefore equivalent. So it might be, right, we don't have a good understanding of this, that for certain natural groups, the decision of Diffie-Hellman assumption is implied by the D-log assumption. But this is one of the old big open problems in public key crypto, right? So people tried to prove this in the beginning, but failed. So in the meantime, people have also constructed groups in which the decisional Diffie-Hellman provably does not hold, whereas the D-log assumption presumably does hold, or it's reasonable to assume that the D-log assumption does hold in these groups. Good. Now we've talked about key exchange. Now let's talk about public key encryption. So the drawback of key exchange is that we always have to interact, right? But many many modes of communication today are non-interactive. Think about emails, right? When I write an email to you, when I want to write a secure email to you, I don't first want to interact with you before I can write you this message. I just want to sort of somehow encrypt the message and send it to you without having to interact with you. So, of course, in with private key encryption, we can do that, right? If we already have a pre-shared key K, we can communicate securely without having additional interaction. So in public key encryption, as most of you probably all know, we introduce a dedicated public key PK, which is used to encrypt messages. And as of course the name suggests, this public key is made public to the world. So if I want to be able to receive encrypted messages, what I'm going to do is I'm going to take my public key and say, put it onto my homepage. Now, what can we do? Let's say Alice wants to send me an encrypted message. That is, she takes the public key, encrypts this message, or this email, and sends it encrypted to me. And I can decrypt it using my secret key, which I now call SK. Instead of K, right? Because we're distinguishing now between a public key and a secret key. We're not just having a key K. Now we're having a public key PK, which anyone can know, and a secret key SK. Good. And yeah, whoops. Well, no, too fast. Good. So now let's talk about the first the syntax of public key encryption schemes. So public key encryption consists of 3 PPT algorithm, keygen, enc, and dec, with the following syntax. So those on the face of it look like the algorithms we had for private key encryption. This was also keygen, enc, dec. Keygen is a randomized algorithm which again takes as input the security parameter encoded in unary, but now outputs both public key and secret key. The encryption algorithm takes a public key and a message and outputs a ciphertext C, right? It doesn't take the, now in the setting of public key encryption, it doesn't just take a key K, now it just takes the public key PK. Okay, here there's of course a typo. Decryption takes a secret key SK and a ciphertext C and outputs a message M. And the first thing we of course require is that we have correctness, right? That's always the most basic thing. Without correctness, we don't have functionality. There's no point in looking at this. So we require that it holds for all security parameters lambda, that if we and all messages M, that we first if we first encrypt M with the public key PK and then decrypt it using the secret key SK, we get back the same message M, where PK and SK were generated by the keygen algorithm. That's, of course, the most basic thing we're asking for. And before we talk about security, let's look at the very first proposal, which was in 1960. 78. And this was proposed by Rivest, Shamir, and Edelman. This scheme is commonly referred to as textbook RSA these days for a reason that we're gonna get into in a moment. So how do keygen, enc, and dec work here? Keygen chooses two random lambda bit primes p and q and sets n to be the product of p and q. Then it chooses a random e from z phi of n, and remember phi of n is the order of the group z, of the multiplicative group of zn, right? That's the phi function, and of course we can compute this as p minus 1 times q minus 1. We've seen that using the Chinese remainder theorem. We choose such a random e in z phi of n with GCD e phi of n equals 1. In basically that means we choose e from z phi of n star. Okay. Now, okay, good. And we compute also this d such that e times d congruent 1 modulo phi of n. So we essentially have d is e inverse modulo phi of n, right? We've seen how to do that using the extended Euclidean algorithm. The public key, let's make it in green, now consists of n and e, and the secret key may be in red of n and d. Okay, so to encrypt a message m in Zn, we just compute m to the e modulo n. How do we compute this? How so phi of n is pretty big, so e is also pretty big, right? So how do I compute this? I can't just say m to the e is m times and so forth times m. If I were to do this with a repeated multiplication, I would be busy forever. This takes exponential time. So someone in the chat wrote already the answer, and that's correct. We do that with square and multiply. So I guess you've all seen that in your algorithms courses. Compute via square and multiply. We compute actually any exponentiation in cryptography via square and multiply. But good. And now decryption, and this is sort of the cool thing about textbook RSA, there's almost the same thing as encryption, right? You can kind of use the same algorithm implementation. You just swap message for ciphertext and public key for secret key. So you just compute C to the D modulo N. And whoops, now the first thing, of course, we have to make sure is correctness, right? So what is dec sk of enc pk of some message m? I think we're I'm going to do this, and then I'm going to make a break for today, and you can do the quiz. So well, dec is just or let's first do enc. That's m to the e modulo n, and the whole thing to the d modulo n, right? The modulo n you can just leave away. We're computing in Zn here. So this is m to the e times d modulo n. Okay, what am I going to do now? how can I see that that this is that m to the e times d is the same as m, right? That's what I have to prove. I need to show that this is the same as m. How can I show that? Yeah, someone wrote it. We know that E times D is congruent 1 modulo phi of n. Okay, but what does it help me? Why is this the same as m to the E times D modulo phi of n? Once we have this, then we know, yeah, okay, this is m to the 1, good. Why am I allowed to reduce modulo phi of n in the exponent? Euler said so, yes, but we've seen that sort of in the last lecture. Exactly. So because phi of n is the amount of elements in the group, right? For now, for this simple thing, let's just assume m is in Zn star. If it's in Zn without Zn star, it still works. But for now, assume that it's in Zn star. Then we do this by the first corollary of Lagrange, right? The first corollary of Lagrange said if the order, if we do an exponentiation in some group, we can always first reduce it modulo the order of the group. But the order of Zn star is exactly phi of n. So that's the reason why we're allowed to do this. And then we see that D is the inverse of E. But okay, I'm going to stop here for now. What we're going to talk about next time is, of course, security of this first of public key encryption schemes and all the problems that it has, right? Why it's not really secure, why it's not really an encryption scheme. But all right, good. Let's leave it with that for now. And I think, yeah, sort of 2 minutes remaining until you can start with the quiz for today. All right, do we still have questions? Are there still? If not, have fun with the quiz. All right. Okay, I'm going to stop the recording now.